So, to summarize what we have discussed in the last class, like this forking and all. So, we have seen a C program that does forking to create new processes in Unix operating system. After fork, there are two different processes running copies of the same program. The only difference is that the value of PID for the child process is 0, while that for the parent is an integer value greater than 0, and which happens to be equal to the PID of the child process. Child process inherits privileges and scheduling attributes from the parent. So, whatever the privilege in terms of file access etcetera it has, and whatever the scheduling attributes like the CPU usage, disk usage, IO waiting and all that. So, whatever scheduling parameters are used for the parent process, so they are also available to the child process. Then after that, child process in the particular example that we have looked into, so it overlays its address space with the Unix command ls that is used to get directory listing using the exec lp. So, it is a variant of this exec system call. So, for overwriting the address space of itself. Now, the parent process, it was made to wait for the child process to complete by the wait system call, and when the child process completes, the parent process resumes from the call to wait, and where it completes using the exit system call. So, basically the child process terminates, and when the child process terminates, so the parent process is informed. So, when the wait system call, it was executing a wait call, so it is informed and the parent process will continue from that point. Now, as far as termination is concerned, a process terminates when it finishes executing its final statement. So, that is the obvious one. So, last statement of the parent process of a process is executed. So, it is over, or it asks the operating system to delete it by using exit system call. So, often this is not visible to the programmer. So, many a time the compiler will introduce some exit system call at the end of the code that is generated for a process. So, that way the process terminates, and this control is given back to the operating system. The process may return a status value, typically an integer, to its parent process. So, that via the wait system call. So, basically sometimes we need to know that a child process that has been created, so what was the outcome of its execution. So, there may be different types of termination of a child process, and this parent process may be interested to know in which way the child process terminated. So, as a result, there can be different outcomes of the child process, and they can be, this outcome can be informed to the parent process by means of this return value. So, when it exits, normally with the exit system call we can assign some return value. So, that return value is passed to the parent process by the operating system. So, parent process will also know how the child process terminated, and all the resources of the process are deallocated by the operating system. So, all the resources that we had, so that is taken back by the operating system. So, this is one possible way. Other possible way, if parent may terminate execution of children processes executing the abort system call. So, sometimes the parent may execute an abort system call, and the children process they will get terminated. So, why is it necessary? So, this may be necessary that child has exceeded allocated resources. So, as we know particularly in Unix operating system, so there is a parent child relationship. So, a user may spawn a process that is taking lots of resources. Okay, so, that may be some either a misbehaving process, or the process may be a highly demanding one. So, that way so that cannot be run at some specific time of the day. So, that may be run only when the system load is low, maybe at night or something like that. So, if such a process has to be aborted, or such a process has to be stopped, then so that is the situation that they have exceeded the allocated resource, and then we want to abort it. Then task assigned to child is no longer required. Many a time, like we start a task, but that task is no more required. So, why do we schedule that task? This may be particularly important, like say suppose on occurrence of some interrupts, so maybe in a real time system. So, a fire sensor has sensed some smoke, and then accordingly something has to be done, but you see that after say 2 or 3 minutes also the appropriate action is not taken. So, there is no point continuing to invoke that task. So, that way we may want to abort that particular task. Other option is the parent is exiting and the operating system does not allow a child to continue if its parent terminates. Like we have got this parent child relationship between the processes. This parent child relationship, so this parent is there and we have got the child process, it has created a number of child processes C1, C2, C3 like that. Now, what happens if the parent itself dies, parent itself finishes, then what happens to these children processes C1, C2 and C3. So, now there can be different types of thoughts. One thought is that the parent is not there, so there is no point keeping the children processes, so they will also terminate. So, this is one possibility. Other possibility is that this parent P that we had, so it was the and it itself was the child of some other process Q. So, if this process dies, then make all this C1, C2, C3 as children of this Q process. So, that is another possibility. And the third option that we have is there is a init process in the system. So, whenever a process terminates and whenever this situation occurs that the process P terminates and we have got all these C1, C2, C3 as the orphan processes. So, these orphan processes, so they are all made children of this init process. Okay. So, since this init is always there in the system, so we do not have any confusion, like the init will not stop until and unless the system has crashed. So, that way we have got this children processes, they can become part of init and continue like that. So, these are the different types of options that we can have. So, different operating systems, so they will follow different type of conventions. So, some operating systems do not allow a child process to exist if its parent has terminated. If a parent terminates, all its children must also terminated. So, this is called cascaded termination, all children, grandchildren etc., all are terminated. So, entire branch starting at that particular process which is being terminated. So, that is they are also terminated. So, this the termination is initiated by the operating system. So, this is one by one all the processes are terminated. Then a parent process may wait for termination of a child process by using the wait system call, that we have seen previously. So, this wait system call, if a process executes, so it is waiting for the children process to be over. The call returns status information and the PID of the terminated process. So, this PID equal to wait status. So, this will be so whichever process it was waiting. So, when this fellow finishes, then PID will have the PID of the terminated process and the status information will have the return value which is returned by the child process. If the parent, if no parent is waiting, then the process is a zombie state. So, so that is we do not the parent was not waiting. So, it may so happen that there are the parent process has created a child process. Okay. So, parent process has created a child process and it was not it is not waiting. So, the parent code does not have a wait call. So, it may so happen that the operating system scheduler will schedule the parent process first and the parent process terminates before the child process comes. So, before the child process terminates. So, this process is not there. So, when this fellow terminates, it finds that I do not have any parent. Okay. So, in that case we say that this process is in zombie state, okay, this process child C. Then so that is there, and if the parent terminated without invoking wait, then the process is orphan. So, when this process is parent terminates, but at that time child is not over. So, child is there. So, child is said to be orphan. So, that we have discussed previously. Next will be now how this orphan zombie. So, these situations will be handled. So, that is operating system designer specific and different operating systems. So, they will follow different type of policies for them. So, you will be getting more idea. So, if you are looking into one particular operating system and how does it handle it and all. So, one possible case we have discussed with respect to Unix, where this if the children processes, the parent dies, then all the children, so they made the children of the parent process of the init process. So, that is one possible option. Next, we will be looking into another very important issue in case of processes, which is known as inter process communication. So, inter-process communication means in a system. So, if there are number of processes and particularly there is parent child relationship between the processes, then they are part of a big system. So, as a result they need to talk to each other, they need to communicate between each others. So, there has to be some communication between the processes. So, these cooperating processes can affect or be affected by other processes, including sharing of data. So, this is the situation that is quite common. If I have got a number of processes which are part of a big system, so they will be communicating between themselves, they will share data and all. Independent processes cannot affect other processes. So, since they are, if their processes are independent, then naturally they may be doing totally different types of jobs, maybe from two different users they are coming. So, as a result, so they are there, so they often, most of the times they do not need to communicate between themselves, they do not need to contact between themselves like that. Now, why do we have these cooperating processes? One is the information sharing, like a number of processes they may like to share information, like maybe there are some communication coming from different different places, and all those information need to be gathered and put onto some centralized server. So, as a result there is some information sharing. Computation speed up, multiple processes running in parallel. So, maybe it is like that we just we have got say 10 sensors sensing the temperature of the room and updating some database. So, maybe all these 10 sensors, this there can be 10 different programs which are doing the operation, and as a result this overall update operation will be done faster. So, this is the computational speed up may be there. Or if we can have some complex computation, so that computation may be divided into several parts. Like for example, if I have got say a system of simultaneous equations, like say a11 x1 plus a12 x2 plus a13 x3 equal to say b1. So, this is one equation. Then a21 x1 plus a22 x2 plus a23 x3 equal to b2. Similarly, a31 x1 plus a32 x2 plus a33 x3 equal to b3. Now, if this set of equations, so if we want to solve the simultaneous equations, so there are some methods, iterative methods for doing that, in which each equation we use for one particular variable update. So, if we reserve the first equation for updating x1, second equation for updating x2 and third equation for updating x3, then these three updates may be given to three different processes that can execute concurrently, and that way we can have speed up, but the updated values of x1, x2, x3 needs to be communicated to the other processes as well. Like the first process is updating x1 and that updated value must be communicated to process 2 and process 3. Similarly, process 2 updating x2 must communicate to process 1 and process 3 the value of x2. So, like that. So, we have got computational speed up, we have got information sharing, we have got modularity also, like maybe the portions which are relatively independent accepting this information sharing. So, they may be divided into different modules, and then these individual modules may be developed by different groups. So, we have got the modularity, and of course, the convenience, the way that we think about solving a problem. So, if we can think about some independent processes, independent cooperating processes, then definitely that will help us in developing the overall program. So, this type of situation, these cooperating processes need inter-process communication. So, this is given a broad heading of IPC, inter-process communication, and operating system must provide some mechanism by which this inter-process communication can take place efficiently. So, we will be looking into some such techniques followed in general operating systems, this inter-process communication. So, there are two different models of this inter-process communication. One is based on the shared memory, other is based on message passing. So, shared memory is like a board. Okay. So, for example, I can say like if I write something on a board, then some other process can see that and it can understand, okay, it is like that. Now, one possibility is that if I write on a board, then that is visible to all other processes, or so everybody in the class can see if we write something onto the board, or if we can have some permission. Okay. So, it may so happen that process A has written something onto the shared memory, but to read the content of the shared memory some permission is necessary. So, if that permission is granted to process B, then process B can only see that data, or similarly if process B writes something onto the shared memory. So, we can have process A can just read it from there. So, of course, what type of access we have, so that is a question. Like in this diagram, so as you can see here, so process A can write something onto the shared memory, similarly process B can also write something onto the shared memory. How do they read it? So, that is not depicted here. So, it is assumed that whenever it is written onto the shared memory, so both the processes are ready to see it. So, this is one type of sharing. Another type of sharing that we can have is by means of message passing. So, this process A, it sends message to process send message to the message queue, and that is meant for process B, and then process B can get the message from this message queue. So, this kernel, so we can have a message queue that has got all the messages coming from different processes, and process B can read that message queue one by one. So, if it is meant for that particular process, so every process will have got a corresponding message queue, and then any process that wants to send a message to another process. So, it must write onto the queue of that particular message, or it can of that process, or it should send the message to the corresponding queue only. And then the receiving process, when it executes some receive type of system call, so it will be reading from the message queue, and then it can take a decision that what type of who is the sender of this message, and accordingly take some action. So, we have got these two type of communication mechanism, inter-process communication mechanism. One is based on shared memory, another is based on message passing. Now, shared memory systems. So, an area of memory shared among the processes that wish to communicate. Now, this shared memory type of communication. So, as you can understand that even if I have got a parent process and that creates a child process, and this parent process has got code, data and stack. Suppose this parent process has got some variable x in it. So, accordingly in the data segment of this parent process, space is allocated for x. So, this is given for x. Now, when the child process is created, so this is for the parent, this child process is created. So, child process gets a copy of the data segment, even if it has not executed the exec call. So, it will get a copy of the data segment, and it will get a copy of the variable x here. But you should understand that this x and this x, so they are totally different. So, if the parent executes a statement x equal to x plus 1, so that will update this x, and this if the child executes a statement like x equal to x into 10, so that will update this x. Okay. So, they are not same. So, basically whenever we create a fork, the data segments that are created are different, though one of initially they are same because they are copy of the parent only. But after that, whatever modification is done to the data segment, so they are for individual processes. So, they are not common between the processes. So, if we really want something is to be shared, that is some variable has to be accessible to both the processes, then I need some special area of memory which will be used as the shared memory. So, if this is my complete memory that I have, maybe in this part I have kept the code, data and stack segment for this process parent process P, and here I have created everything for the child process CH. Now, if I want that this x value of x will be visible to both this parent and child, then I should create this x in a region of memory which is called the shared memory. I should create it into shared memory, the variable x here, and somehow make somehow ensure that both P and CH can see this shared memory location x and can manipulate or modify it. So, this is the job of the shared memory. So, how this shared memory is implemented, that is operating system specific, but this has to be there. So, an area of memory shared among the processes that wish to communicate, that should be there. The communication is under the control of the user's processes, not the operating system. So, this is a facility that is provided by the operating system, but which processes will coordinate and how they will coordinate, in the sense that it may so happen that this parent process. So, it will just it will write onto this x, and the child process, it will only be able to read from this location x, but child process will not be allowed to write onto x. So, this way there can be different types of read write permissions that can be there. So, this control of this communication should be in the hand of the user processes and not by the operating system. And major issue is to provide mechanism that will allow the user processes to synchronize their actions when they access shared memory. So, when so major issue is that maybe when this parent process is updating this x, this child process is trying to also read the content of this, but that way it will get some inconsistent data and that will create some difficulty. So, somehow we have to have a mechanism by which we will be taking care of that. So, before coming to this, so let me clarify something with respect to Unix operating system, how this is the shared memory is done. So, in case of Unix operating system, what happens is that, as I said, that there is a shared memory location. Suppose this is the shared memory space of the full memory. So, I will try to explain like how two processes they can make sure that they are accessing the same memory location, same shared memory location. So, we have got this shared memory divided into, say, suppose I have got a number of locations in the shared memory, and each location is accessed by some key value. Okay. So, suppose I have got process P1 and process P2 and they want to share the variable x between them. So, what this P1 will do? So, P1 will be executing a statement which is called shared memory get. So, it will be executing a system called shared memory get, and here it will mention some key value. This key value is nothing but some integer value, and then it will also mention some permissions, some read write execute permissions that that should be there for the shared memory key, for the shared memory, and of course, the size of the shared memory. So, how many bytes that you want to have. So, suppose I mention this key value equal to 100, what the operating system will do is that it will use a hash function, where input is this 100, and accordingly it will generate an index in this range. Okay. So, it will just suppose it generates an index of say 55. So, as you know, the hash function is nothing but say one possible hash function h of key may be key percent table size. So, key percent table size. So, in this case suppose I give a value of 1000 and my table size is say 50, then it will fully divide it. So, say table size is say 55. So, it is 1000 divided by 55, 1000 divided by 55. So, this will be 11, this is 200. So, this is 1, 18 and remainder is 2. So, it will be it will come to this 2 remainder will come. So, this value will be equal to 2. So, if you give it 1000, so this is location 0, 1, 2. So, it will be pointing to this one. So, this key value giving a value of 1000 will ultimately mean that I am talking about the shared memory location 2, and this permission I will give the read write execute permissions, like how the other processes will see this particular location, and the size, like how many bytes that we want. So, maybe we want say 4 bytes. So, this 4 bytes will be created. So, this these are the 4 bytes that are there. Now, P2, for P2 also it will be using a SHM gate with the same key value. So, it will also mention key value as 1000 and permissions and this size. So, other parameters will be there as I said. So, since both the processes they are using the same key value. So, for both of them they will point to the same location. So, P1 will also point to this and P2 will also point to this, and depending upon the permission that we have set. So, there may be read write execute permissions. So, as a result they may be allowed to modify, read or write, etc. So, this is how this in case of Unix operating system we make the processes to share some memory location which are not part of their their data segment. So, this x variable which is not part of the data segment. So, this is this actually returns some ID, and then there are a pair of other calls like SHM AT and all. So, by this you can attach a particular variable to this particular ID. So, that can be done. So, I am not going into that. So, for more detail you can consult Unix operating system interprocess communication primitives, but what is required of course is the synchronization between this parent between these processes, like one process is say maybe modifying the value of x and another process is trying to read it or write the data. So, as a result it can lead to data inconsistency. So, we have to somehow ensure that the data is consistent. So, maintaining data consistency, it requires mechanism to ensure an orderly execution of the cooperating processes. So, if it is half done, half update is done, then naturally the content of the data will be inconsistent. In this direction, so we will be looking into one particular problem which is known as producer consumer problem, where we have got some producer process that produces some information that is consumed by a consumer process. A typical example may be an user is pressing keys of the keyboard. Now, that key has when the keys are being pressed, so that is there is a keyboard process which reads the values, and there is another process another program to which the values are sent. So, that way we have got this this keyboard process and this other program that is executing. So, there is a communication between them. So, the producer consumer process, the keyboard process is the producer process and the reader process is the consumer process. So, we have to have some sort of buffer for communicating between them, and then the buffer may be unbounded buffer or bounded buffer in nature. So, we will continue with this in the next class.